Grüezi. We are in the basement or the base of Tor Alva, the White Tower. So this one is a 3D printed tower about 30 meters high, and it's actually much more interesting than your general 3D printed house. It's made out of concrete and it's considered to be the tallest 3D printed building in the world. So this tower stands in the little town of Mulegns. According to ETH, only 11 people still live here. So this one is done as a research project, an architectural project, and also it's a cultural venue. What I think is very interesting about the base is, of course, this is all poured concrete structure, but it actually rests on top of a very old historical building. It used to be a blacksmith, especially a hoof blacksmith, because through this little town here, there was basically a line of public transport by horse carriage, and this was the blacksmith that took care of the hoofs. So they placed the whole tower on top of this building, but of course they made a huge fundament to carry the weight of the tower itself. The tower itself weighs about 30 metric tons. So the 30 meters is actually including the existing base, and you have about 32 of those structural columns everywhere. It's 8 per segment, and overall it's 124 segments for the whole tower. On the top there is a approximately 8-meter high dome where about 32 spectators can enjoy a theater experience, for example, because you have concerts and theaters going on here as well. So this is much more interesting than your typical I bring a 3D printer to a site and print a house, because those columns were actually not manufactured here. They were largely printed at the ETH, so at our university in Zurich, and there they printed or prefabricated those parts. And you see the top and the bottom are very smooth. So they were actually manufactured using classical concrete pouring, and just the columns itself were 3D printed. The really interesting thing about it is actually not the 3D printing itself, but the rheology behind the material. Because you have to understand, if you print the first layer and the next, you have to have a material that extrudes well enough, but it can support what comes above it. And of course, it's concrete. There is a lot of weight added. There was also a second robot that added steel rings inside of it to give it its structural integrity. One thing that is very special about this tower is that actually the concrete itself is the load-bearing part. So you don't have a steel structure inside that carries the load. They put a steel structure in for the reasons of like just structural integrity, but the load-bearing part is actually the 3D printed material itself. So developing this kind of material, especially in this color, was the really hard feat, because it's not painted. They actually chose their sands and mixtures in a way that allowed them to directly print white concrete. So let's talk about slicer settings. So here they used a layer height about 10 millimeters. The whole tower, the closest approximation I could find, was about 2,500 layers stacked on top of each other with 1 centimeter in height, so 10 millimeter, and approximately 15 to 20 millimeter in depth. And yes, those are actually, like I said, load bearing. So in some manufacturing of buildings, you see them printing this as kind of like a lost form, and then they pour cement in it or concrete or whatever and put steel in it. But here you only have this shell, and you can actually see that if you look down here, because they left little escape holes on the bottom of every column because of temperature changes in the air. So if temperature changes, of course, you get moisture that collects on the inside, and this has to go somewhere, otherwise it damages the structure itself. But those are still hollow. You can also see some of those little lines here where it looks like a print error or a layer shift. So this is actually done because their 3D printer had a specific height it could go to. It was done via robotic extrusion, and they manufactured those segments and then they put them together. The bottom and the top are poured concrete, like this part is poured. And this was done because you need the accuracy to be able to mount it together. So this whole building is basically an assembly. You can screw it. Oh, no, you can screw it. You can disassemble it and assemble it somewhere else. So part of this project was also to show that you can do architecture that is temporary, that can be taken down and built up somewhere else. And you can actually see those screw points up on the top, for example. So you see that all those printed columns, they go into a poured mold and then they are screwed together. But the molds itself for the poured concrete, they were 3D printed as well. So their normal plastic extrusion was used to generate the molds that then the concrete was poured in to harden it and to make it really fit well. So this hybrid approach in manufacturing is much closer to the actual usable manufacturing techniques that can make it into mass production than simply printing a whole building out of a 3D printer just because you can. It's using additive manufacturing where it makes sense, and it uses classical manufacturing to add to it and make it really usable and viable. And I think that is great. That's how 3D printing should be used, where it makes sense. So let's talk about design. And I'm not talking about the design of the columns itself yet, but I'm talking about the design of the whole tower. Why does it look so ridiculously organic? You can think that it's just architectural preference, but there's actually a reason behind it. So this computer was computationally developed. It is a structure optimized or a topology optimized structure. So concrete was only used where it's really necessary. A computer developed this on like the statistics or the statics that it had and on physics. And it basically just uses material where it is needed. And I think this is one of the points this building is trying to make. We have to save material, especially because concrete is one of the biggest CO2 emitters out there. So using less of it is better. But if we can use as little as possible while not jeopardizing structural integrity, that's even better. And this is, of course, where additive manufacturing shines. In conventional concrete manufacturing, this structure would be insanely expensive because of the formwork. If you want to pour concrete, you need a form to put your concrete in. And this is a lost form. You use them once normally because you break them apart. And with 3D printing, you just slightly change the toolpath and you can use one machine without formwork to just simply print out whatever you want. The ETH itself describes two levels of ornamentation. So for one, you of course have the layer lines and you see they are drooping everywhere and you can think like, okay, oozing, over extrusion, but they are there deliberately. They didn't try to hide the fact that it was 3D printed. They wanted to make it clear. They wanted to use it as a form of style. And then there is another thing. There is, as you can see, this like spiral pattern everywhere. And when you look at this tower on the top and everything, you are kind of reminded on the little cake toppings you have on wedding cakes. And this is absolutely on purpose because the little village of Mulegns is world famous for their Zuckerbäcker. Zuckerbäcker means they are confectionists and they do these sugar sculptures since hundreds of years and they're actually world famous for it. So there are sugar bakers from here that made it all the way to Italy, France, and that are famous for their sugar works. And so this tower should also pay homage to this as well. But it also pays homage to the Baroque building styles that you have in Graubünden, which is the state this little town is in. So the ETH stated that additively manufacturing those columns saved them about 50% in concrete. And there is another thing when you look at the money side of things. Concrete is cheap. Labor and formwork are very expensive, but also concrete itself, like I said, produces the most CO2 on any building site. So with this technology, they can use what is cheap and leave out what it is expensive and also basically do something good for the environment at the end. So additive manufacturing addresses two problems at once. It can additively put material where it's needed and it can also eliminate complex formworks. The material was a research project in of itself. ETH Zurich worked together with BASF and Knaus, among others, to really develop a wide robotic extrudable concrete mixture that can also take structural load. So you have to see when you develop a material for something like that, the rheology is super hard. You need to develop a material that will harden fast enough when it came out of the nozzle, but it will not harden so fast that it hardens within the nozzle. It has to be soft enough when the next layer comes around to really bond your interlayer adhesion, but it has also to be strong enough to have the structural support of the layers above it. And this is where concrete 3D printing struggles the most right now, is to find this correct material behavior. Some
manufacturers actually have to pause their print after they printed 3 or 4 layers to let them dry for a few hours, and then they continue. But this introduces weaknesses every few layers. So you want a material that you can continuously extrude, that bonds to each other, but it gets hard enough and strong enough at the bottom to support the top. There's another problem that many of the earlier days 3D printed houses now face. Because this material is such a fast hardener and dryer, it actually develops a lot of internal stresses. So that's why you see in some of the first project houses that were printed already huge cracks through the facade. And here, of course, in a structural load-bearing application, that would be absolutely devastating. So this tower wasn't just manufactured in 2025 and that's it. The ETH actually worked together with Origin. That's the cultural foundation that paid for it and that made this project possible and thought of it. And they worked together in 2017-18 and they already produced some of those 3D printed columns as kind of like a theater piece that would stay outside. And this was actually meant, of course, as decoration, but also as a longevity test for the concrete itself, to see how it would behave if it's like set out into the weather of the Alps. So all the printing actually span around 900 hours and was done over the course of about 4 months of real production. It was produced in the ETH and then, of course, carried here and assembled. So these columns that were test printed are still in place and you can still visit them in the city of Riom, where they're still used as a tourist attraction and for theater play. And if you ignore the biggest marketing claim of the biggest 3D printed structure in the world, it's actually way more than that and way more interesting. It's a combination of computational design, about art, robotic extrusion, material development, modular components, assembly and transport. So it's a real feat of engineering made possible with additive manufacturing. And like I said, this structure was actually planned as a temporary fixture. So this tower itself will only stand here for 5 years and 1 year is already over. So if you want to come here and have a look at it yourself, you have to speed up. After that, nobody is sure what will happen. Probably it will be dismantled and maybe built up somewhere else. I really recommend that you come here and see it for yourself. Touch it. You can book a guided tour where it will explain you the history behind it, why it looks like that, and a lot about this little small village in of itself. And I mean, there's always one reason more to come to Switzerland. I mean, look at that nature.